introduce. My name is Dewanyomo Widiasa, NPM 2231501. Here I will explain about the electrical power system components. Introduce to electrical power system. System components over 5 of power distribution network and substitution, explaining of generation, transmission and distribution system, improve of transformers and protection device in power system, explain of different type of electrical power system. Electrical power generation. Benefit of power generation. Electrical power generation is essential for meeting the energy demands of modern society. A different mix of energy source ensures reliability and resilience of the power grid. Renewable energy source help reduce greenhouse gas emission and combat climate change. Challenge of power generation. Certain methods of power generation such as coal-fired plants can have negative environmental impact, meaning an extraction of fossil fuels for power generation can lead to habitat destruction and pollution. Nuclear power generation shares the risk of accident and long-term reduction with stronger resource. Powerful transmission lines, high voltage tower. Transmission lines move electricity over long direction efficiently and reliably. The lines can span hundreds of miles supported by Thursday towers. High voltage in necessary for power to travel great detention with minimal loss. Maintenance and monitoring are crucial to assure continuous power delivery. Power distribution network over 5 power lines form a network that transfer electrical from power plants to substation, transformers, step down high voltage electrical to a safe level for homes and business. Grid maintenance source reliable power delivery to meet customer demand and prevent outgas. Transformers in power transmission voltage control device. Transformers adjust voltage level for efficient power transmission. Step of transformers in cars voltage for long distance transmission. Step down transformers decrease direct cars voltage for safe distribution to homes. Transformers are essential for maintaining grid stability and power quality. Understanding substitution key power facilities substitution switch control protect power system efficiently. They play crucial role in electricity distribution network. Substitution consists of transformer, switch, and circuit breaker operating at various voltage levels. Substitution ensures reliable power supply. Capacitor in electrical system. Capacitor reduction power loss, improve efficiency, and stabilizer voltage level. Capacitors store and reals and energy to help maintaining consistent voltage across circuit. Switch basic power control gear. Switch gear in essential for managing electrical flow in power system. It introduce circuit breakers, fuse, and other protection device. Switch changer ensure safety by isolating faulty equipment from the rest. Proper maintenance of switch gear is crucial for system reliability. Electrical power system key component and function. The primary component include generators, transformers, and transmission lines. Function involve generating, transmitting, distributing, and controlling electrical. Thank you.
Suppose we have a long wire with 2 points in it, A and B. At T equals T1, if we apply voltage pulse to the point A, assuming the wire being perfect conductor, what is the voltage at point B at same instant of time? From circuit theory, since the wire has no resistance associated with it, there is no voltage drop across the wire, and the voltage at point B is equal to that of point A at the same instant of time. But this is not true. This is valid only if the signal travels across the wire with an infinite speed. But in reality, signals cannot travel faster than the speed of light. So the voltage pulse will reach the point B at instant t2 after some amount of delay. That delay is known as transit time. Transit time results in a voltage difference between point A and B. So there is always voltage difference between any 2 points on the line, due to the finiteness of the speed of the wave. we can minimize that difference in voltage by decreasing the wave frequency. In other words, the higher the wave period with respect to transit time, the less would be the voltage difference. Transit time is equal to the distance traveled by the wave over propagation speed, while the period is equal to 1 over frequency. Hence, to minimize the voltage difference between point A and B on a wire, the length of the wire between point A and B must be very small compared to the wavelength. This concept is applied to any electrical component. If the length of the component is large compared to the wavelength of the signal, then we can't ignore the transit time effect. To make Kirchhoff laws valid, we must meet the conditions. The circuit element must be so small compared to the wavelength of the signal. If we divide this wire into smaller and smaller sections so that each section is too small compared to the wavelength, the transit time effect would be negligible over each section, so we can apply low frequency circuit analysis. That wire is called transmission line, a path carrying electrical energy from source to load. Consider a transatlantic cable running from the US to the Great Britain, a good example of uniform two-line transmission line. If we short the other end and measure the input impedance, it looks like a big inductor with series resistor modeling the wire losses. Similarly, if we leave the other end open, the input impedance will look like substantial shunt capacitor, two very big conductors separated by the electric. Due to the conductivity of the shields and the seawater, there is also a shunt conductance associated with the cable even when left open. Since the distance is too large, even at very low frequencies, the signal wavelength would be too small compared to the wire, and the delay would be significant. So how do signals propagate through this cable? Well, each transmission line, as we just see, is composed of series inductance and resistance, and parallel capacitance and conductance. Let's model the cable by them, then analyze the circuit. In other words, lumping the total inductance, capacitance, resistance, and conductance along the wire into idealized concentrated components with infinitesimal dimensions and connecting between them with perfect conductors. This is known as lumped element model. Using the lumped element model here gives us completely wrong answer. Even at very low frequencies, the large series inductance would act as an open circuit, whereas the large shunt capacitance would make the wire a short circuit. For the lumped element model to be valid, the signal wavelength must be very large compared to the circuit element. We can divide the total series and shunt impedances into smaller and smaller sections of very small dimensions compared to the wavelength. Let's ignore the losses for the time being so that we can remove the series resistance and the parallel conductance from the model. And here comes the problem. For 1 centimeter long section, we would need more than 500 million inductors and capacitors. Even the most efficient simulator running on the most powerful computer can deal with that. So how did people solve this problem when the first transatlantic cable was laid out in 1857? Well, have you heard about infinite ladder networks before? This model is an infinite ladder network, with Z1 and Z2 being the impedances of inductors and capacitors respectively. Using the input impedance equation of the infinite ladder network, then the input impedance of such a cable is having that form. Since each section is only 1 centimeter long, inductors and capacitors are too small and can be neglected, making the input impedance equal to the square root of L over C. Observe that if we choose to terminate the ladder network with an impedance of Zn, then the input impedance remains the same. The behavior of a finite ladder section terminated with Zn is indistinguishable from that of the infinite network. So for a lossless transmission line, the voltage wave will see a real impedance while traveling through the wire. This impedance is known as characteristic impedance. If the line is terminated with load of that impedance, the characteristic impedance would not change. Now, we started by lossless elements, inductors and capacitors, and end up with real impedance. Does that mean that the lossless transmission line dissipates energy? Actually not. The circuit is made up of lossless components. We have two scenarios here. If the line is infinite, the signal will travel through it indefinitely. It is dissipated from the generator perspective. If the line is terminated by resistance equal to the characteristic impedance, the signal travels through the wire and gets dissipated in the load. In both cases, the generator feels injecting the signal to resistance equal to the characteristic impedance. So far so good, but how the injected signal itself propagates through the line? Now to answer that question, let's analyze one section from the line. Even at very high frequencies, the signal wavelength would be very large compared to the section dimensions. Hence, the lumped element model is valid, and Kirchhoff laws can be applied at each section. The analysis is very simple. Just applying voltage signal to the input of the section, and measuring the change in voltage and current across the element. I'm not gonna bother you by the equations, but the final result is these forms: voltage and current wave equations, where gamma is called propagation constant, a characteristic quantity of transmission lines. It depends only on the line parameters. Wave equations are simple differential equations telling us that at each point in time, each point in the line has different voltage and current based on its location. If we assume that the voltage and current vary sinusoidally with respect to time, the solution of the wave equations is consisting of forward traveling wave and backward traveling wave, where alpha and beta are the real and imaginary parts of gamma. Let's ignore the backward one. We're gonna cover that in a separate video when we talk about reflections. Now alpha represents the losses in the wire. Let's ignore it by ignoring R and G in each section to have a lossless line. Taking the real part, we notice that the voltage and current vary sinusoidally with respect to time and distance along the wire. Notice that the current wave is the voltage wave divided by the characteristic impedance. At each instant of time, each point on the line has different voltage and current. By fixing the distance and varying the time, it feels like the signal is moving along the line. What we're doing here is just plotting the voltage variation along the line at successive instants of time. Here we assume that the line is lossless, meaning there is no attenuation in the signal while traveling through the line. Voltage and current at each point in the line vary sinusoidally with respect to time. You can notice that by seeing the movement of the dot up and down, where the height of each dot represents the voltage at that point in the line. Don't forget that the forward traveling current wave is just the voltage wave scaled by real number, the characteristic impedance, so it varies along the line the same way as the voltage. Notice that when we change the distance and fix in the time, it turns out that the signal is moving with respect to time. Meaning for a lossless line, each point in the line sees a delayed version of the signal depending on its location on the line. The larger the distance from the generator, the higher will be the delay. That delay is a function of distance along the line, and is linearly proportional to beta, the phase constant. If beta is equal to 0, there wouldn't be any delay along the line. Beta is equal to 2 pi over the wavelength. That confirms that the larger the wavelength of the signal, the less would be the delay. In the next video, we will use the simulator to get more insight of what's happening inside the transmission line itself.